Swayam Prabha. Digital India. Educated India.
Here is what our dynamics is all about. Our dynamics will have rigid body lumped mass systems, will have a flexible body systems, it will have autonomous systems, and it will have non-autonomous systems. What are autonomous systems and what are non-autonomous systems? What is flexible body, what is lumped body, and then everything will be divided into linear and non-linear. So at the end of it, it is all linear and non-linear. If you know what are linear systems or non-linear systems and how to work with linear and non-linear systems, you can move on in that. Okay. So what are rigid body or lumped mass systems? And how does it differ from flexible systems? As we said, the electromagnetic system is a rigid lumped mass system because we assume the mass is concentrated at a point. Okay. Whereas for a beam, the mass will be all through the beam. So they are flexible systems. So that's the difference. A flexible system will be governed by a partial differential equation of motion, whereas a rigid system will be governed by a ordinary differential equation of motion. Okay. And therefore, it's easy to solve a rigid body system than a flexible body system. So when you have a lumped mass system, when you have a flexible system, you try to convert the flexible system to lumped mass system to make sure that things run faster. Now, you can have autonomous systems, you can have non-autonomous. Autonomous systems are general systems that you see, and non-autonomous systems. Autonomous systems is generally time invariant system. That means the properties are not changing with time. Non-autonomous systems are whose property will change with time. That is time varying system. That means mass is changing with time. For example, in a rocket or aeroplane, right? Whereas for time invariant system, the parameters will remain constant. So mass, stiffness, damping will remain constant all through your simulation. Okay, so they are different from system where mass, damping or stiffness changes with time. If they change with time, they are a bit difficult to solve. That's all, nothing else. And all these systems can be divided into linear and nonlinear. Linear systems are where your solutions can be added up to provide a solution for a different input. For example, if you have sine omega t as input, you have an output. If you have sine omega 2t as an input, you have an output. If you have a single signal which is sine omega 1t plus sine omega 2t, then your outputs can be added up. That is linear system. For non-linear systems, you cannot do that. So if you have a sine omega 1 input, you will get an output. If you have sine omega 2t as an input, you will get another output. But when you have both the signals together, your output will not add up. That's a non-linear systems. And that's why they are a little bit challenging to solve. Whereas linear system is very very easy. So you have series of inputs, you can add up the series of outputs. No problem. Okay. So that's how it differs. So we will solve them and see how to solve them. So this is a single degree of freedom system in a linear system. A spring and a damper system, you can see the mass. If you have a magnetic mass, it will keep moving within the solenoid. If you have solenoid, in the white space is a solenoid space, then it will keep moving in that and you can generate power. So this is a very simple system, as you can see. And its equation of motion is given by mx double dot plus kx equal to 0. You can do balance of forces on both sides of the mass. They can be upward, they can be downward, they can be sideways. All these three different things, all of them will have same equation of motion, mx double dot plus kx equal to 0. What is mx double dot? Mx double dot is the mass into acceleration, is the inertia force, and kx is the force restored by the spring. Summation of those two will be 0. Okay. If you have an excitation, that excitation will come on the right hand side. So this is how you write the equation. I think if you do the free body diagram, you can do it. We don't need to do it. We can write the equation of motion is like this. So even if you have downward, no problem. Gravity, action of gravity is not taken into account in equation of motion because you assume your response from an equilibrium point. So the equation of motion of a free undamped single degree of oscillator is given by this, and then you do a mass normalization. That means you divide by mass on both the sides, right? You divide by m on both the sides, you get omega n square, which is the natural frequency of the system. So this parameter omega n root over of k by m. So you divide k by m here. So it becomes u double dot because m is vanishing now, and this becomes k by m. So k by m is omega n square, and that is called natural frequency of the system, and that is very important for any system. It is like your natural characteristics. Okay, natural characteristics. You behave differently when you are in front of your friends, and you behave differently when you are in front of your parents, right? Guardians. Ayana. So your natural characteristics comes out when you are with your friends, and when you are in front of your parents, it becomes a forced system. So forced oscillator. So that's not your natural characteristics. Okay. All right. So natural characteristics is natural, while it is under free vibration. No force is given onto it. Whatever it shows, it's a natural property. Okay, so we call it canonical form. The equation of motion is linear because there is no term of u which is higher order than 1. Okay. If you have u square there, then it's a nonlinear system. If you have u double dot square there, it's a nonlinear system. Or u cube, whatever, it's a nonlinear system. As long as the power is 1, it's a linear system. And it's a constant coefficients. That means it's a time invariant system. Omega n is not changing with time. Omega n is independent of time. And it's a second order in time. That means u double dot is there, and two constant of integration is needed. Two initial conditions are needed, right? You have to integrate it. You have to integrate it twice, and if you integrate twice, you get two constants of integration, and therefore you need two initial conditions to solve. So this is an initial condition problem, okay, not a boundary condition problem, right? So now you assume, right? You assume your solution u of t is some exponential form. Right, C to some exponential form, and then you put it back into the equation of motion. So it has to satisfy the equation of motion. Once you do that, you get this equation, which is called eigenvalue equation, right? Eigen equation, and then you solve it. You get your natural frequencies, I omega n, and therefore your solution. You see that you get two solutions because it's a quadratic equation. You get one is I omega n plus, one is I omega n minus. Since it's a linear system, I can add the solutions. So my complete solution is C1 e to the power I omega n t and C2 e to the power minus I omega n t. Since it's a linear system, I'm telling again, you can add the solutions. Non-linear system, you cannot do this. Okay, which can be now converted very easily. If you remember your class 12 mathematics, plus 2 mathematics, you can convert it to A1 sin omega n t plus A2 cos omega n t. Now we said that we have two constants of integration here, A1 and A2. We have to make them a part of initial conditions. So you put the initial conditions that initially the velocity, the displacement was u0, so it comes out to the a1 to be u0, and initially the velocity be v0. Then your a2 omega n becomes your v0. You have to just put them there, right? So you put t equal to 0, right? If you put t equal to 0, u of t is u0, which means that your a1 is u0 because sine 0 is 0. Then you take derivative. You get u dot is equal to a1 omega n cos sine omega t plus a2 omega n cos omega n t. Then you put t equal to 0, you get this term there, not term that term, and then you get v0 by omega n is your a2. So if you solve it, you get these two equations. So your final equations in terms of initial conditions is this. You see, we are using both the initial condition u0 and v0. To solve a differential equation of second order, you need both initial conditions u0 and v0. Both velocity should be known and displacement, the position should be known. Now, based on omega, you can have, so this is for damped system. I think this was for undamped system. Now for damped system, you have two things. Your natural frequency changes to minus zeta and omega n t plus minus I omega dt. Right? So omega d is a damped natural frequency. It is given by omega n 1 minus zeta omega. And then your time period in damped time period becomes 2 pi by omega d. Omega d is damped natural frequency, which is slightly different from a natural frequency. This is your natural frequency, this is your damped natural frequency. Okay. So there is a slight difference, 1 minus zeta square. And this is your solution. So you could see the solution. In the solution, previously the solution was a1 cos plus a2 sine. Now you have a damping part added to it. We will do that. This is the undamped system. Undamped system, the amplitude never changes because there is no damping. There is no loss in energy due to damping, and therefore the amplitude will never change. Amplitude will remain same, and as you can see here, the amplitude remains same of the motion. Okay. You move on, you have to add a little bit of damping to it, you see the amplitude is reducing exponentially. Okay, exponentially the amplitude reducing. Here also if you see, the mass was moving initially a lot and then slowly it has come down to 0. So if you have a damped system, your natural frequency, your motion comes down to 0. Electromagnetic systems are damped system because you are taking energy out of it. It is vibrating and it is creating electrical energy, right? So it is taking energy out of the system. So it will get damped with time. You have to keep giving energy input to keep getting your energy output. Okay? You cannot think that I have an electromagnetic system, I give a tap only once and it will all through its life, it will keep on giving you energy. No, it doesn't happen. It will come down to 0 because it will lose energy through electricity. Okay, anyway, when you have critical damping, that means your damping is very high, almost 100%. System just goes down like this. Okay, I'll run the slide again. System just damps, doesn't move up and down. If you're over damping, it go very slowly, it will go. Okay, so damping plays a huge role. So all of them together. So dynamics, sir, this much is enough. We'll now put them. We know the equations of motion now. Mx double dot plus Cx dot plus Kx equal to 0. We'll write a MATLAB code and run and see these curves are coming this way or not. Before that, let us go. This is a dam system. Dam system we just saw the natural frequency of the dam system is like this. So under damped, over damped, and critically damped cases are all there. So their solution will look like this. We'll solve our under damped case also. So remember these solutions, and this is the response that you get. So this is your undamped case, black one, and then you have slightly damped as your violet color. Then you have green, critically damped is a red, and very heavily damped is the green. It shows the frequency driven response. Frequency driven response of the system. So at 0 natural frequency, at 0 damping, you see, at very low damping, you have very high amplitude of response. And your phase is almost 180 degrees apart after and before. But with slight damping, it can come down. So as I said, if you have little bit of damping also, or if you put it away from your natural frequency, your power can come down very heavily. So what you do, you try to do resonance on a system. That if the system resonates, you get high power output. For undamped system, this is the power that changes with resonance. So you can see the amplitude grows very fast. For a damped system, the amplitude will go and then become fixed. It will not go to infinity. Okay, so the stress will come to a constant. It will not keep on growing. Again, this is also a beats. You have heard about beats in your musical systems. It's also a resonance, part of resonance and anti-resonance. I think we'll now code the thing. Yeah, finally, if you have continuous system, this is what happens in a continuous system. This is your first mode of a beam, simply supported beam. This is a second mode, this is third mode. This is all string, like a string, they will attach if they are very flexible, right? And this is what you have to take care as a safe function. They are not single point motion. And their motion, as you can see, is distributed along the whole body. Okay, this is we'll learn in the fourth day, how to model this with a PZT attached to it and solve. Okay. So you could see here there is no single point motion, this is all distributed motion across the beam. And since these are all distributed across the beam, they are called distributed or flexible system motion. Right. You could see the first one is first mass, first mode. Second one is a torsional mode, twist. Third one is I think second mode, second bending mode. I don't know what is the fourth one. It can be something. It is also looks like, it is going up and down. First mode is up and down. Okay. So you have multiple modes and you have to take care of all these modes when you model these kind of distributed structures. So now Subhanshu will show us how to start modeling in MATLAB the linear systems and non-linear systems.